Good morning, everybody. He's Michael, and I'm John, and we're both really excited to share our results on the distribution of discriminants over a finite field. I'll begin by addressing a very important question. What exactly is a discriminant? A discriminant is a fundamental quantity that we associate with each polynomial. For example, I'm sure many of you are familiar with b squared minus 4ac, the expression under the square root in the quadratic formula. This is actually the discriminant of the quadratic polynomial ax squared plus bx plus c. Well, as it turns out, if we take any polynomial, even if its degree isn't 2, we can always define its discriminant. And the way we do that is, let's say we have a monic polynomial f of x. Then we define the discriminant of f to be the product of all the differences of the roots of f squared. In our research, we focused on discriminants of polynomials with coefficients in fq, the finite field with q elements. An example of such a finite field is the integers mod p, where p is a prime number. Throughout this presentation, we'll use the symbol fq bracket x to denote the set of polynomials with coefficients in fq. The structure of finite fields has been extensively applied to other areas of science and engineering. The discrete logarithm problem over fq, for example, has been used as the foundation for many cryptological methods. The properties of the polynomials in fq bracket x have been employed by many error-correcting codes, the most notable being the Reed-Solomon codes. These are used today in many commercial products involving the storage of data, like DVDs. They're also currently being used by NASA to communicate with the robots exploring Mars. The specific topic of discriminants over FQ has been studied for over a century. In 1898, Stickelberger proved that for an odd prime p, the parity of the number of irreducible factors of a polynomial with coefficients in the integers mod p is completely determined by two things: the degree of the polynomial and whether its discriminant is a square. The result was generalized in 1962 to hold in all finite fields of odd size. And as a corollary of the Stickelberger-Swan theorem, discriminants of monic polynomials are equally distributed between the non-zero squares and the non-squares of fq whenever q is odd. The Stickelberger-Swan theorem was a monumental result describing the distribution of discriminants over fq. It was incredible. Due to the theorem, we now have that there are equal numbers of polynomials with square and non-square discriminants. So a natural question that follows from this is, what about equal distribution at the level of individual elements of fq, rather than between the squares and the non-squares? And this problem was left wide open for over 50 years. Recently, a research group at the 2014 Arizona Winter School proved that discriminants of monic polynomials tend towards a uniform distribution over all of fq, as the degree tends to infinity. This was a breakthrough in this area of study, but it said nothing about the distribution of discriminants in specific degrees. Today, we're going to tell you all about how we address this curious problem. We'll show you some startling patterns that Michael and I continue to be amazed by every day. And we hope that all of you share in our excitement by the end of our talk.
Here is a table showing discriminant counts for monic polynomials in f5 bracket x, 4 degrees 2 through 10. We shaded columns with all numbers equal, and as you can see, there seems to be a pattern of 2 shaded columns, followed by 2 unshaded columns. This is amazing. Take a look at column 10. The numbers are huge, yet they are all exactly equal. What is going on here? I mean, the definition of the discriminant is a monstrous product, so we'd expect monstrous results, like column 9. But no. Instead, we see a pattern suggesting that if the table is extended, half of the columns will be shaded. Why should any of the columns be shaded, let alone half? It's really weird. And what's more, we have tables for other values of Q, all of which show similar crazy patterns. Take a look at this table for Q equals 7. We see a pattern suggesting 1/3 of the columns will be shaded. And this table for Q equals 11, it's almost all shaded. These tables suggest there may be a bigger structure out there, which explains these weird and wonderful patterns.
Michael and I spent countless hours staring at and studying these tables, trying to find this bigger structure. And we were finally able to identify and prove a surprisingly simple pattern that tied together all of our previous observations. In our tables, we noticed that discriminants of degree m monics are equally distributed over FQ whenever the greatest common divisor of Q minus 1 and m times m minus 1 is 2. For our first main result, we proved that this condition is always sufficient for equal distribution whenever Q is odd. For even Q, we modified our condition a little bit to have the GCD equal 1 instead of 2, and we proved that this condition is also sufficient for equal distribution. These results lead us to a startling conclusion, that for all Q, there exist infinitely many degrees with equal distribution over FQ, and the gaps between these degrees are actually always bounded by Q minus 1. This means that the patterns Michael just showed you will actually continue indefinitely if we extend the tables. To prove theorems 1 and 2, we came up with a useful change of variables method that allowed us to compare sets of similar polynomials with different discriminants. What we did was, for a non-zero constant c, we defined a function gamma c to send a polynomial f of x to c to the degree of f times f of x over c. A key property of gamma c that we used is that if a polynomial f has degree m, then the discriminant of gamma c of f is equal to c to the power of m times m minus 1 times the discriminant of f. This is where the m times m minus 1 in our GCD condition comes into play in our proof. Choosing C to be a generator of the multiplicative group of FQ, we use gamma C as a map to create a perfect matching, so to speak, between two equally sized sets, each containing polynomials of a common discriminant. For example, we show here the action of gamma 2 on the monic degree 2 polynomials in F5 bracket x. As you can see, gamma 2 sends all the discriminant 1 polynomials to the discriminant 4 polynomials, and it sends all the discriminant 2 polynomials to the discriminant 3 polynomials. This action was the central idea for our proofs of theorems 1 and 2.
We've looked at equidistribution, yet there is an even more basic pattern in the data. Notice that none of the numbers in the table are 0. Is this always the case? That is, for any m, do the discriminants of the degree m monic polynomials in FQ bracket x take on all values in FQ? For large degrees, the answer is yes. In fact, for degree m greater than or equal to the characteristic p of FQ, we constructed a family of polynomials whose discriminants take on all values in FQ. We have several cases to consider, and we sketch the proof by looking at the case when p doesn't divide m. The family of polynomials, fa, is shown where a, which is arbitrary in FQ, is one of the coefficients. By direct computation, we express the discriminant of fa as this function of a, such that as a runs through all values in FQ, the discriminant of fa also runs through all values in FQ, showing the surjectivity of the discriminant. To conclude, our results are significant for these reasons. Our equidistribution condition leads to an explicit classification of infinitely many degrees with equidistribution. Our results go well beyond the previous results of Stickelberger and Swan. We also proved the surjectivity of the discriminant for degrees greater than or equal to the characteristic of FQ. Our work paves the way for future research on the statistical properties of discriminants, including the questions, Is our equidistribution condition necessary as well as sufficient? And is the discriminant surjective even for degrees less than the characteristic of FQ? Finally, our work on exact equidistribution in specific degrees complements recent work on the asymptotic distribution of discriminants done at the Arizona Winter School. Refinements of our results and our novel change of variable method have potential applications to coding theory and cryptology. Our work would not have been possible without many people. We thank our mentor, Professor Keith Conrad, for suggesting our project. We thank Glenn Stevens and the Promise program for hosting our research over the summer. We thank the Clay Math Institute for helping fund our research. We thank Stephen Kwong for creating the computer programs to generate our data tables. We thank our Promise counselor, Zhaorong Jin, for guiding us through the early stages of the project. We thank the Siemens Foundation, Discovery Education, and the George Washington University for this chance to present our research. Finally, we thank you, our audience, for your time and for listening to us. These are our references.